Okay, so draw yourself a really good picture of a piston in a cylinder. Now, if your picture is not quite as nice as mine, don't despair. Remember, I'm a trained professional. Okay. So here's this piston rod. In here is our gas. So when we talk about all these things like heat and internal energy and work, it's always from the point of view of the working gas. Okay, there's a gas in there. I'm going to even write gas in there so you know there's a gas in there, right? Okay. Now, lots of things can happen to this gas. The temperature can rise or fall. So this, when we talk about change of internal energy, okay, this is an increase in internal energy. Okay, that's the increase of internal energy. What is internal energy? And internal energy is the aggregate kinetic energy of the molecules of the gas. Right? Imagine adding up at some instant all of the 1 FmV squares of all those particles bouncing around inside the cylinder. Right? That's what it is. Aggregate just means add them all up. Right? It is proportional to temperature. Okay, so U is proportional to temperature, because really it comes from something like MCAT, right? When we talk about MCAT, that's what we're talking about, is the internal energy of something, yeah? So if the temperature rises, then the internal energy rises, and if the temperature falls, then the internal energy is falling, right? It cannot change. You cannot change the internal energy without changing the temperature, yes? Because that's what it means. How's that? Yeah? It's like there we have it, right? But it's in joules. This thing is in joules, right? The next thing that can happen, right, is that we can have heat added to this system, right? Okay, so this is heat added. And by the way, this is a positive change of internal energy. This is negative, and that's the whole trick, right? Positive is increase, negative is decrease. Okay? This is heat, here is heat added to the system. That's positive, right? Okay. Negative would be heat flows out. Yeah? Okay. So you could draw a little picture here. Heat flowing in, this is positive Q, right? Heat flowing out, negative Q. Another pen. Okay, so positive is heat flowing in, negative is out. And then the final thing, by the way, right now this is like an MCAT problem, isn't it? Right now we have a formula that says Q is MC delta T, right? But there's a third exciting thing, right? The third exciting thing is that we can do work. This engine now can do work, right? So W is work done by the system. Now, I don't know if you recall, but we did this whole thing with work. When we talked about work, do you remember how I talked about how I do work on the mass? Yeah? I push on the mass and the mass goes up. That is positive work, yes? Does that make sense? Okay. What was it though when I was pushing up on the mass but it moved down? Negative work. The force I'm exerting is up, but the displacement is down. This is the same thing for this thing. The piston is pushing up because of course gases always push on the piston. It will always be pushing on the bottom side of that piston. So when it moves up, that's positive work, right? That's work done by the system. Okay. What if we push it down? If the cylinder moves down, which way is the gas pushing on it? Or the piston moves down, which way is the gas pushing on it? Up, but it's moving down. They're in opposite directions, so that's negative work, yeah? Does that help? Right? So work done by the system is positive, right? On the system is negative. This is positive work where the piston moves out. right? This is negative work, piston moves in. Now, think about your car. Think about your car for a second. Are you thinking about your car? If your car is powered by an internal combustion engine, if it's not an electric car, okay, isn't there a fiery hot thing called the, what is it called? It's called the power stroke, I believe is what it's called, isn't it? Where the piston moves out. It's ignited the gas mixture. The piston moves out under high pressure. Yes? Are you picturing this? That's what propels your car forward. Is there an in-stroke, though, where the car actually is slowed down by the engine? Yeah, it's called the compression stroke. Engines always have both of these. Isn't that a little weird? Right? There's a compression stroke, and that's, of course, what provides the braking power. When you don't give it gas, it still has to compress the air, and that's what slows it down on a hill. That's what gives your engine holding power. Right? So cars have both of these cycles, and that's what we're going to talk about. We're going to head there. Okay? Now, let's do an example problem. Are we ready for this? Oh, I'm sorry. I got to give you the formula for which we're going to do an example problem. Right? So here is the formula. Q is, if heat flows in, then it could cause a change in internal energy, or it could cause the engine to do work, right? So basically, if we take this away, it's just MCAT, Q equals MC delta T, right? But if we allow it to do work, then things get a little more exciting, right? Heat could flow in, and we could let the piston move out, and the choo-choo train can go forward, yes? That's at least a little bit somewhat exciting, isn't it? Yeah? Okay. So let's look at our, right, so now I set it up there, right? If heat flows in, I made a little English sentence out of that. If heat flows in, the gas gets hotter, the temperature rises, and or the gas does work, the piston moves out, right? So you could write that down. That's a handy. You need a. Thank you. That's what people are always saying after school. You need a ride? Don't say that in the UK. You need a ride? Don't say that in the UK, because ride means something in the UK that you probably don't want to. I don't even know. Okay. I haven't figured it out yet. Okay. So here's our energy thing. This is conservation of energy, isn't it? We're just saying if heat flows into a heat engine, we burn coal, we burn gasoline, right? This thing is going to, the gas is either going to get hotter. In other words, we don't let the piston move, the gas gets hotter, right? Or we let the piston move and it does work, right? It could possibly get hotter and do work, but, well, anyway, I'll show you this, okay? There's any combination is possible, right? So you need a riot does 45 joules of work compressing a gas. So it sounds like we're doing positive work, but if the piston's moving in, if you're compressing it, what's true about the work? Yeah, it's definitely negative, right? So I'm going to put a negative 45 here. Why is it negative? Yeah, the piston's moving in, right? It says that on there. But I try to make it look like it's positive, don't I? I did my best. But language failed me, you know? Right? 23 joules of heat flow out of the gas. Nothing tricky about that. Which one of these is it? Flowing in or flowing out? Yeah, it's negative, right? Okay. So this is minus 23. And then it's like blank. Hopefully we don't fail at this math, right? Blank has to be.
I'm going to say, what is 22?
What is 22 is correct, yeah. 22 joules, right? Okay. Now let's answer the second question. What happens to the temperature? Is it hotter or colder? Hotter. Why do you know it's hotter? Yeah, it's compressing but heat flowed out, right?
Wouldn't that make it colder?
Well, I know. So there we go, right? So now it's a question, right? We compressed it. Really, we did this much work on the gas. This much flowed out, but this much was retained by the gas. That's another way to think about it, right? Here's how you know that the temperature went up. You don't need to like really ponder it too much. If the delta U is positive, temperature went up. If it's negative, it went down. Okay, yes? So since it's positive, the temperature went up. Okay? Now,